26, the one, 22 and 26. 22 like we did in class? It's the same formula and everything. It's the square root of 16 minus x squared. The only difference. Oh, did they use rectangles or? You didn't double it for 22 though. It was the half.
Yeah. I'm talking about what we did in class.
Yeah, from what we did in class, right? Circular cross sections, yeah. But we'll run through it again in just a second. Yeah.
You know what? I don't know for a 5
Because you're a bit lazy at times.
No, I don't have over. Well, yeah, I don't have over a 5 because of it. I'll get like a 88. I've had like 88 before because I'm not lazy this year. I was like as a freshman and a sophomore. I was lazy.
All right, let's look at 26. Will it not reach if you set it? Well, there you go.
That's even worse.
I wouldn't say lazy. No.
When you showed up at class,
All right, let's look at 26, guys. The nose cone of a rocket is a paraboloid. Paraboloid? Yeah. Don't ever feel like that because most of the time it's wordy, but it's not asking you anything really difficult. All right, so it's revolved about the curve y equals square root of x. So there's square root of x. Of course, there's negative square root of x down there on the bottom if we include that. We're going from 0 to 5, and it says partitioning it into 5 subintervals of equal length. So if I go from 0 to 5, 5, and so this comes in, and it's even showing you that each, it's got that nice picture in there. Did y'all see the picture? I'll show you. Good. A Christmas. Both of my kids did. Okay. Okay. Kenzie skied, but Parker sat in the lodge. It was like ice because. Okay, so if you look, they've already got the picture drawn here. 1, 2, 3, 4. But didn't they say 5? Oh, they didn't do one for 0 because it's 0. The radius will be 0. Everything will be 0 here. So we're going to do the volume of these 4 circular cross sections, and then we're going to add them together. So this is going to be a bit of an underestimate of the volume because you can see all the spaces here that I'm lacking. It's a left, yeah, a left end. It says the subintervals left endpoints at these points. Remember the one we did in class, we did the midpoint. The midpoint makes more sense to me. If I were doing this and it was not told to me what to do, I would have gone in at each midpoint. But I think that the reason that they're doing this is because it'll be a little easier with the equation here to do with the whole number. I did, yeah. This morning, I did this morning. Okay, so let's do it. How do you find the volume of a cylinder cross section like that? Times. So the width here each time is 1, right? Because it's 1. So, right. So the volume of this, so we got pi r squared times that height or that width. I'll make that width. And so I'm going to do that for each one all the way through, right? Okay. So I need to know the r. That's the variable in question. The width is going to be a constant 1 every time. That won't be hard. Pi is obviously a constant as I go through there. But what is my R? My R is what is changing each time. So to find the radius, remember that is halfway. So the radius at 1 is what? Well, I'm not going to use the midpoints. I'm just going to use the 1. I'm going to draw it from here. So this cylinder, the radius is coming from the 1 here and going up. So I need this y value. So the square root of 1 is 1. So this point is 1, 1. This point would be 2 square root of 2, right? This point would be 3 square root of 3. This point would be 4, 2. And I don't need the 5 because I'm going left endpoint instead of right endpoint. So here to find the area, so the area of each section here, or volume, I'm sorry. The volume of this first one would be, remember radius here is 1, so it's just pi. The volume of this one would be, no you don't because your radius is squared. So it's 2 pi, but what's the square of 2 squared? It's just 2, yeah. So the volume of this one then, I hope you see the pattern. And then all I have to do is add them together. The volume of the whole thing is 1, 3, 6, and pi. Units cubed, I don't know what here wasn't specified. We didn't do the 5 because it's the left endpoint. So if I did this one that's kind of non-existent, it would be 0 pi. Yeah. Yeah. Multiply it by what? 4?
Oh, yeah, so, yeah, 19.
The times in minutes, but the velocities in seconds. That's why.
Yeah, 19.
That's why you got to look at those units. So 19, the time is in minutes, but the velocity is given in meters per second. So you're going to have to convert one of the two. You either have to convert the minutes to seconds or the seconds to minutes. And then it should be easy from there. So, yeah. I would convert these to seconds before I did it.
Convert that to seconds.
So I'd multiply it by each one by 60, yeah.
Oh, that's 11. Because the answer's in the second.
Well, you're looking for, well, that's the seconds, yeah, that's your conversion there. Mhm. Yeah, that was all for 26. It was a. That's okay. All right, 22. To estimate the volume of a solid hemisphere of radius 4, imagine its axis of symmetry to be the interval 0 to 4 on the x-axis. Partition it into 8 subintervals. I don't think we did 8 in class. What did we do in class? We did 4 in class, didn't we? Okay, so.
We did do it.
Oh, that's right, but we did 8 for the whole thing, but this is just, okay. So here, each one's going to be a half, right? The width here is, yeah. Yep.
When it looks like that, when it's half, it's supposed to be half. Like on that side, but on the other quadrant. Go over the it was top half.
Yes, because it specified it being a semicircle of rate. It didn't give us an equation. We came up with that equation. This tells us that we're just using this portion and gives us the equation. So it's a little bit different. But partitioned into 8, so I need to do 4 minus 0, which is 4, divided by 8, which would give me the 1/2 width, right? So that's what tells me each one is 1/2. So then it says approximate the volume of the solid with cylinders based on the circular cross sections of the hemisphere, which is really, really wordy just to say to do it the same way that we've been doing it. Absolutely. So that part A says to find the sum of the volumes of the cylinders, and do you expect S sub 8, which is just the sum of the cylinders, to overestimate or underestimate? Well, you can look at it and tell over, right, based on the picture, because they're overhanging the, and this is obviously telling you to do a left endpoint. Did y'all recognize that? Because of the, you see the points on there? They're wanting you to do left. Again, we did mid in class. Exactly. That's exactly right. All right, so as I do this one, I need to know, remember it's volume is pi r squared times that w. So this is the same in every single one, right? The only thing that's changing is my radius for each and every different cylinder. So what I'm going to say is the volume of everything when I sum it together, I'm actually going to go ahead and pull out this 1/2 pi, because that's going to be in every single one, right? And so I want the radius squared when x is 0, and then the radius squared when x is 0.5, and I want the radius squared when x is 1, and I want to do this all the way until I get to the radius squared when x is 3.5, because I'm left endpoint, right? Yeah. Yeah. The y values? Does it work for that one? It would. Check and see that. That'd be interesting if it does. I'm thinking yes, but do a random equation on your calculator and then run the program on it where it'll give you left ram, right ram, and M-ram, and then average the two together. You know what I'm talking about? Okay, so now let's go through and find it. So I got 1/2 pi times. So it's the square root of 16 minus x squared. So square root of 16, which is 4, right? So the radius is going to be 4. What's the radius when x is 1/2? It's going to be nasty, right? Y'all are looking like whatever. I think we found that yesterday. No. Let's do this. When it's 0, when it's 0 is 0. When it's 1/2, 1/2 squared is 1/4. Oh, 4, sorry. Yeah.
Okay, I was looking at y.
Yeah, we're looking for the radius here. I'm gonna, now when I find this radius, I'm gonna leave it under a radical because I'm squaring it over here anyway, right? So this is just finding the r. So technically what you could do is you could say, well, r squared, which is what I'm looking for, right, is 16 minus x squared, and just find that. Don't worry about that radical. Does that make sense if I do that and just leave that off? Do what? Because over here, I'm going to be squaring them every single time, and when I do that, it's going to cancel that radical out. So I can do it now or then. It doesn't matter when. Just to say my... So 16 minus a quarter. What do you get? Give it to me as an improper fraction. 63 over 4. And then at 1, because I'm going to have to add them all together, so it'll be, well, there's a decimal. I just didn't want a rounding error, just in case. I know. Y'all hate fractions in general. This is, this is 15. Right, so here I got 4 squared plus 63 over 4 plus 15. Let's keep going. So 3 halves, 1 1/2. But it's squared, so minus 9 over 4.
29 over.
You checked out of this?
16 minus 1.5 squared is 6,004.
Yep. And then at 2, the whole numbers are a little easier. 16 minus 4, which would be 12. It's not gray. Yeah. And this would go a lot faster. You could really use your calculator to make this go a lot faster. I'm just kind of going slow to make sure you understand. Square root of 16 minus 25 over 4. $39 over 4. At 3, 5. I squared them in this column. Remember, because they were under a square root, right? That's right. It's not. As you finish those, part B asks you to express the volume minus our estimate as a percentage. What? I don't know. Well, we did it exact. In the book, they say it's approximately 146.08406.
That's with the 1/2 pi?
Yeah, that's with the 1/2 pi. So understand what they're doing is they're showing you that by doing these cross sections, we're still coming close to, it's an estimation for the volume. It doesn't give us the exact volume. We have formulas for exact volume, right? How do you find the exact volume of a sphere? Then divide by 2 and multiply by pi. Yeah, what? I'm looking it up. 4/3 pi r cubed.
I knew it was weird. I remember that.
Remember, they're going to give you, unless it's a basic formula, if you need it, they're going to give you something like that. All right, so 4/3 pi r cubed. The radius, what's the radius of the whole sphere? Look back at this.
Why were we doing pi r squared?
We were finding the volume of the cross sections of each. Now we're going to compare that answer to the volume of the entire sphere, which is a whole circle. Wow. Okay, no, because what we're doing, what they're trying to get you to see here is, we found the volume of each of these little rectangular cross sections. Like if you think about a three-dimensional ball and taking a knife and just slicing slices out of it, right? We found the volume of each slice and then we added those slices together. But what happened is it gave us kind of an overage. So what they're wanting you to do is compare to the actual volume of that sphere. And we have a formula for that, and we can do 4/3 pi r cubed to compare it to see how it compares to the actual volume. So the radius of this whole sphere, if you think about this being a sphere, right? But it's only half a sphere, do you agree? Right? Because if this equation is going to give us an entire sphere's volume. Right. Right. So I'm going to do, the volume of the whole sphere is going to be 4/3 pi. The radius we said was 4 cubed, and then I'm just going to divide all that by 2 when I'm done. And I'm going to compare it. I don't know.
Yeah.
4/3 pi times 4 to the third divided by 2, 134.0419 units cubed. So if you look, did what we thought was going to happen. There was supposed to be an overage. It is an overage. It's a pretty significant overage, I think, but still an estimate nonetheless. All right, y'all need a little break before we... Yeah. The Riemann monkeys, aren't they? Isn't that one of the ones that they tested with diseases and stuff? I think I am. Okay, I think you're right. I think I look like an idiot right now. Okay, let's just move on. Scratch that conversation. I think you're right. In fact, I'm about 99.999% sure that you are right, Katie, and I am wrong. I am just going, that is not true. We have 30 whole... Which doesn't take much right now. Okay, let's talk about Riemann sums real quick. I think it's rhesus monkey. It's not. I messed up. All right, so the big thing here, we're still doing the same thing. We're still partitioning into subintervals. We're still using that to estimate areas and volumes. But we're going to use some sigma notation. I don't know if you guys remember this. Did y'all get to that in geometry with the little sigmas? Or did we do that in algebra 2?
We did that in,
I did it in algebra 2 with one crew. We got to it when we got to sequences and series. But I don't remember if it was y'all's crew or not. You covered for algebra 2 with me?
Yeah, I did.
I thought we missed so much.
All right, let's start. Let's start first with an example, and I'm going to do it the way we know how to do it, and then I'm going to show you how to write it in summation notation using Riemann sum. So let's say I have this function. One single bat. That's not true.
It's the blue lines over there. third one, I-
Dylan, you get me so off track.
No, I don't want to do that, but I mean, sometimes
Let's say I asked you to find the right, and instead of the right rectangular approximation, all that, we're going to call it the right Riemann sum, because that's actually what it is. It's just the Riemann sum, and that's just using the rectangles to approximate it. But let's find the right Riemann sum here. Let's do it by hand first. And I'm going to introduce a little bit of new notation here to you, so just stay with me. It's kind of new, but it's not really new. The first thing I want to know is, what would my width of each of these rectangles be? Now, what'd you say? Yes, it's a half. It's a half. Good job. So my width of each one, we know we take the biggest x minus the smallest x, and we divide it by the number of intervals we want. So we get 2 over 4, which is a half. So that means the width of each one. So I'm going to now call this delta x. That's what my x is changing from each rectangle. Do you agree? Would it make sense to call it delta x? Okay, so let's say delta x. Actually, you're ahead of the game because delta x is actually dx. That was actually what I was going to get to in a minute, but since you said it, that's perfect. We'll go ahead and say delta x is the same thing as dx. That's right. And that's going to come into play, I'm sure you know. Really soon. Yeah. Well, if integrals are antiderivatives, then, you know, they're backwards and forwards. Okay. Yes. So delta x is the width of the... Everybody okay?
that was just fine.
You do the x max minus x multiplied by the number.
Right. Right. If I asked you to estimate the area, you do what?
That's how many times over the question.
This is how many intervals you want. That's your number. I'm sorry, I didn't hear you. You gotta look me in the eye and say, Miss Wakey. I'm sorry. I never ignore, it's not intentional, I promise. Okay, here we go. So now find the area under the curve using a right Riemann sum. But does it matter? Do you have to know what it looks like?
No, really don't.
Really, you don't,
You can just plug in.
right? So what I'm doing, remember, the area of each one. What's the width of each one? So I'm going to do delta x, and then I'm going to times it by what? I'm doing from the right, and each one's a half, so let's think about it. From 1 to 3, if this is 1, and I'm going by a half, so there's 1.5, 2, 2.5, 3. It helps me sometimes to draw it out like that so I see. So if I'm going from the right, here, 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 and here. So it's going to be right. F of 1.5 plus F of 2 plus F of 2.5 plus F of 3. You agree with that? Right? And so this is the same thing you were doing with the table. You're just coming up with it this way instead. So to find this area, I'm going to do 1/2 times. Well, remember, it's e to the x, so it would be e to the 1.5 plus e squared plus e to the 2.5 plus e cubed. Mm-hmm. But the point of this is not really that you find the answer just yet. I'm using this as an example to kind of tie in.
Oh, wait.
I mean, you can if you want to. Yeah, go ahead. Yeah, find it. Find it. Yeah, find it. Thank you. That's much fun.
What's
2.71. I always just put in the calculator. Now, what I want you to see is how we use summation notation to write this. So I'm going to assume y'all don't remember summation notation, and let me just take just a second to remind you of how we do this. So what we'll have is we have this big sigma, capital sigma. That indicates to us that we are supposed to sum some things together. No, it means sum. And so it'll tell us where to start at the bottom, maybe I equals 1, whatever it is, and it'll tell us a value to go to up here. Let's just say it's 10, okay? And then we'll have an equation here. So maybe, and this has nothing to do with this example, this is just a side note here, if you didn't know. Maybe this was 2i. What this would say is this would say, okay, so take 2i, plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, and add all that together until you get to 10. Yeah. So this would say, start with 1. So you'd have 2 times 1 plus 2 times 2 plus 2 times 3 plus, huh? Yes, from 1 to 10. The equation is 2 times, right? So 2 times up until I is 10. Right. Right. Right.
Well, what if they want you to do
Right. Right. Right.
well, how do you know?
Or if this was 2i plus 1, then, or let's say 2i plus 5 plus 5. So each one of these would have a plus 5 on it too. What do you mean subnumbers?
0 to 4, but they want you to have it separated. Like how do you know how many times they want you to separate? You know what I mean? Like if the interval's 0 to 4, and they're like, I want you to separate it. All right, they say I want you to partition.
We are going to use the function itself. I'll show you. Just so you see what, this is just to show you what, but I'll get to that. I see what you're saying. Right. Right.
Oh, wait. So is it 10 times or is it?
It's from this number to this number, and you're plugging in here, okay?
Like, if the interval equals to,
Okay, yes, and then
13 times 6, just over 10.
no, not your. I think okay.
Wait. So the interval is not like you don't go by 3.
Huh?
Like you would just start at 3
And then
go to whatever. Yeah. 4, 5, 6, 7, 8, 9.
Oh, okay.
Yeah, okay.
It's not like the interval.
Right. Okay, sorry.
That's what
Clearly, we did not do this in Algebra 2 whenever we did it. Okay, that's okay. That's all right. These are 99% of the time, these are going to be a multiple choice question where they'll give you the summation notation, and you have to find a solution for it. Just so you know how to. Okay, okay. All right, so what we're going to do, if we took this same summation here, which is a summation, you see what's happening, right? We have delta x, that's our width, okay? I'm going to use that in my summation. So what I'm going to do when I write, maybe I should title this summation. In summation notation, yes, just so you see what it is. Now we still have to define f of x. So we know f of x is e to the x. We're given all the same information that we start with, right? But here what I'm going to do, this is going to tell me how many intervals I want to break it into. Okay, I want 4 subintervals. Okay, this is your n. That's your n up top. Yes. So how many subintervals do you want? I want 4 subintervals. Okay, because I showed you that so you know how to work it. Don't just stay with me. This is saying you're still going to have to find all the same stuff you found before. You're going to do it the same way. This is just a way to notate it, to write it.
Wait, is that I like this side?
That's a subscript. Yeah, that's a subscript. And I have to times it by delta x each time. There's a reason we're introducing it this way to get you used to this notation.
There's no way you can just show you to the whole side of each and then have it with the half of after.
You're saying it's half at each time.
Add them all together with that.
Or you could have done 1/2 e to the 1.5 plus 1/2 e squared plus, right. You could do it either way, right. Okay, so this is saying you're going the first 4 x's in your interval, okay? It's still, you couldn't, if I just gave you this, right? And then I said, let f of x be e to the x. Here's what you would need to understand from that problem. I need to find the area under the curve with 4 subintervals, but I would still need to tell you that I need it to be from 1 to 3. You see what I'm saying? All of this would need to be given to you, and then you would jump straight to here.
That wouldn't make any sense because it says I equals 1. You can't have 4 subintervals.
It's not I equals 1, so it's saying x sub 1 plus x sub 2, x sub 3. Well, x sub 1 would be when x is 1.5. Don't get real caught up with this. Don't get super duper. Okay, let me give it to you in general. In general. Not those. Okay, that was just with me showing you what summations do. Just hang tight. Okay. This tells me my number of intervals. Yes? That's the first thing. All you need to know, and this will be the same every time you're asked to do a Riemann sum. This literally says do delta x times, or if you want to do it together, we can do it together. Delta x times f of x sub 1 plus delta x times f of x sub 2. Right? Because I got to go, and I keep doing that until I get to, it's the same thing with those first, that 1 plus I or whatever it is, x sub n. It's just a different way to write it. That just tells you to start at 1. It's just, that's your, yeah. Right. These are always going to start at 1 for right now. For right now, just assume they are always starting at 1. Right. They're going in for the I's, and it doesn't have anything to do with f of x right now. The only thing it's saying is you keep doing this. That is correct. In our example, x sub 1, which was the very first, was 1.5.
And will it tell us?
So this would be x sub 1, x sub 2, x sub 3, and x sub 4. Yes, all that would be. That stuff is still given to you. And the problem's still done the same. It's just the notation. It does. We're going to use it for something like is why. We're going to kind of, but you need to.
So, what if you had, if you didn't have to split it up, maybe you could verify, like, if it was 0 to 4, you would get by 1, like the x of 1 would be 1.
Yes, yeah.
And then if you had to split it into more,
These are always going by ones. Because that's your number of intervals, because you're not going to split it into 1.5.
Like, if you have to, like, if you have to split it into more decimals, like, if it's only the interval, if it's only from 1 to 2.
Right, it could, right. So it could be by 0.25 for each. Yeah, it definitely could. I know. Yeah. Are y'all with me? A little bit? Sort of. Okay. The more we do them, the more it'll make sense. Just so you know. Almost. It was not hard. I didn't think it was. It's multiple choice. Okay. Just note this, and we will come back to this as we do a few things. Let me show you. We have homework. We are going to do something, just not right this second.
Okay, that does make sense.
It does make sense to you. Well, the more you close in that gap, like the closer you get to the widths being 0, right? The closer you get to dy. Let me show you how to write this as an integral so that you can do a couple problems for homework. What's an integral, you ask? All right, y'all ready? I don't think I've showed you this before. Remember, we're still talking about area under the curve. This is actually a definite integral. Here's what this tells us. Find the area of f of x. Now we've only used Riemann sums, right?
what is that?
That is an integral. I know, that's why I'm showing you. Okay. This is the area under f of x. This is what this means. From A to B. Okay, so this is my lower limit. We actually call it lower limit of integration. And that's important that you know which one is supposed to be the lower, because we'll get into some things where we start switching them up. Oh, how did you know? It's not always like that, but for right now it will be like that. That'll always be your starting point. That'll always be, but sometimes we'll go backwards with it. So we might, if that value might be bigger later on, but we'll go back. But yes, that's where you start. That's your lower limit. This is called, yeah, we'll always do. This is called the integrand. The integrand, okay? The f of x. The f of x. Just so you know what it's called. We got this. That's all. Now I'm going to show you how to write the. Watch how easy this is. Just trust me. Just trust me.
Okay. You remember.
Tell me what this means.
Okay, the interval is 1. I mean, wait, we're going
Well, you
by
didn't tell us how many you have.
I didn't tell you how many intervals,
I can do it.
but I still want you to explain. I have n intervals.
Yeah.
Okay.
You plug in 1 into the K.
Okay. Okay.
We don't know what
We don't, but I'm finding the area under what curve? I'm going from 0 to 2. I'm finding the area under the curve from 0 to 2 of what function? C squared, a parabola. That is all this is. There's some different variables in here, but that's all this is. Now, I use K instead of I to be an I. Now, if I throw this in there, I want as many subintervals as I can get. Because the more subintervals I do, the more accurate my estimation is. So, an integral is not an estimation. So if I write this as an integral, okay, it would literally take forever, it would. As an integral, this would say, go from 0 to 2. My function is x squared. Remember that dx gives me that width each time. This is the same thing. Which way? So what you'll be doing tonight is you'll be taking them from this to this. I told you, stay with me a minute. There's a reason. It doesn't matter. Well, in this case, remember how derivatives we tried to approach 0, my limit to 0, because I wanted the width to be 0. In this case, I want the intervals to be infinity. So my width is kind of a conceptual thing. That's my dx. I'm trying to get that as big as I possibly. You see what I mean? My width as small as I possibly could, so that my intervals are infinity. Because this would give me the exact area under the curve, as opposed to an approximation. No, we will do some solving tomorrow. Tonight, I'm just going to have you do page 296, 1 through 13. Some of them you're really going to have to think about when you look at them to figure out that function. Try not to look at the answers, though, because there's really not a lot of work with these. It's more looking at it and